Hi, and welcome to the OzGrav YouTube channel. Today, we are happy to bring you the next in our live stream talks from our OzGrav researchers. OzGrav is the ARC Center of Excellence for Gravitational Wave Discovery, and we are headquartered in Melbourne, Australia. Today, we are going to bring you a talk by Debatri. She is a third-year PhD student at Swinburne University of Technology, and she is a member of the OzGrav collaboration. She is extremely passionate about physics and about as equally passionate about reading and dancing in her free time. Her talk today is about the physics of gravity. And I would like to now pass off to Debatri to share her talk.
Thank you, Jackie. Hello, everyone. I am Debatri. I'm a part of OzGrav, and I'll be talking about physics of gravity today. So what's so special about gravity and why it's so fundamental, and how physics allows us to understand it more. So to start with, I will start with a short story, which is hypothetical but true. So we have two twins on Earth, Fred and George. They look exactly alike and they're twins. However, Fred is more adventurous. So what Fred does is he decides to board a spaceship and go on an intergalactic tour. Meanwhile, George waits for Fred on Earth. He keeps waiting, and one day Fred returns. However, George sees that he's really old because a lot of time has passed, but Fred is still really, really young. So what is happening? So physics tells us this is true. So what happens to time, or is our understanding of time is something that we need to revise once again. So for that, stay tuned to this talk. So for the first bit, I'm going to talk about something called Newtonian gravity, which was given in the late 17th century by Isaac Newton. And then I'll move on to something much modern, which came on in the earlier 20th century by Albert Einstein. So the first part, when I begin talking about Newtonian mechanics or Newton's gravity, the first thing that we need to learn is Newton's laws. So Isaac Newton gave 3 laws, which we can say were the cornerstones of physics. And the first law says that a body that has some mass will continue to be at rest if it is already at rest, or it'll continue moving with a constant velocity if it was moving with a constant velocity, unless it is stopped by an external agency. So the bodies, they seem to have something very, very stubbornness ingrained in them. And this property, the stubbornness of the body to continue doing what it was doing, is called inertia. Second thing we learn from this law is that a definition of something called a frame of reference. Frame of reference is something like an observer who is allowed to apply the laws of physics, or in this case, Newton's laws, which will follow the next laws. They're allowed to use it in its own form. So when we define as an inertial frame of reference, it means it is an observer who's either at rest or is moving with a constant velocity. Moving on, we come to the second law. This states that there's a body which again has mass m, and if it was at rest, it is getting acted upon by a force F, which is making it change its state. So if it was stationary, maybe it begins moving, or if it was moving, maybe it is stopped or forced it to run at a different velocity. So we define a quantity called momentum, which is the product of mass and velocity. And this external force is defined as the rate of change of momentum. So we need some mathematics into this and a lot of calculus, but don't worry, I'm not going to talk about too much of mathematics, just some basic stuffs, which states that if we do all the calculation, it gives us that this force if the mass of the body is constant, will be equal to the mass of the body times acceleration of the body. So what is acceleration? Acceleration is the rate of change of velocity. So what we understand from Newton's second law is that force is an external agency, and time, we have some notion of time because this rate of change of velocity, which we define as acceleration, when we talk about any rate of change, we think about the notion of time, how it is evolving over time. So this notion of time is ingrained in Newtonian mechanics to be independent of the observer. Doesn't matter if I'm running, doesn't matter if I'm standing, I will record a time which is always same. And if you're running and I'm stagnant, you'll record the same time as I'm recording. This actually comes from something called Galilean transformation, but we will understand more of its functionality later on. Moving on, we come to Newton's third law, which says that a body, if pushes or gives some kind of force to another body B, then body B in turn will push body A back equally. So for each and every action, there is an equal and opposite reaction. So we have this thing called action-reaction pair. Now it is to be remembered that action-reaction pair never act at the same point. Body A, say for example, is pushing body B. So the force of body A is acting on body B. And body B in turn is pushing back body A, but this reaction force is acting on body A instead of body B. So these are three Newtonian fundamental laws. Moving on, Newton also spoke a little bit about gravity, or what gravitation is. He stated that any two bodies just having masses will attract each other with a force. And how? This force of gravity is given by the product of the two masses divided by the square of the distance between them. And there's a constant term in front of it, the whole term is multiplied to it. It's called the universal constant of gravitation. And this term, this is very tiny, 10 to the power minus 11 means 1 divided by 10 followed by 11 zeros. So this is a very, very tiny value. So this means we need very big masses to actually have bigger force of gravity, or we need the masses to be very close to each other to give a sizable gravity. So basically what we understand from Newtonian gravity is that gravitation is a property of matter. It is attractive, always attractive. It acts instantaneously. There is no time lapse, there's no time delay in between the forces actually coming into action. And that it is quite weak from this constant of gravitation. Moving on, let's think of the classic situation of an apple falling from a tree. So the tree is on earth and the apple is just falling, and we are going to use Newtonian gravity. So here we just applied Newton's laws, and then what we see is, so earth is very big, and we make an assumption for the next step is that the radius of the earth is too big compared to the height of the tree from the earth's surface, which is true. And if we look at these three terms, the mass of the earth, the radius of the earth, and this g, universal constant of gravity, these three are constants. The apple's mass can change depending on what apple is falling from the tree. So we can just pretend that these three quantities together form a constant, and we are going to name it acceleration due to gravity. Why acceleration? Because it basically looks like acceleration as well when I was talking about acceleration, because force equal to mass into acceleration. And we find that the force that the apple is experiencing is proportional to this g as well as the mass of the apple. Awesome. However, there's a problem over here, because we learned every action has an equal reaction pair. So if the apple is falling on the earth, why is the earth not getting moving towards the apple as well? Because they are attracting each other equally, right? Newton gives the answer as well. We again use forces mass into acceleration. So we break down the two into quantities. And we see that the mass of the apple is very tiny compared to the mass of the earth. So for this equality sign to be valid, we need the acceleration of the apple to be much higher than the acceleration of the earth. So no doubt the apple is also pulling the earth towards it equally, just the acceleration of the earth is so tiny compared to the apple that nothing actually happens. Nothing calculable or nothing observable actually happens. Uh, so we learn from this whole thing is that gravity is a force. So Newtonian mechanics was the fundamental cornerstone in physics. That's how it all started, we can say that. But just by giving laws, a physical conjecture is not proved. So we need experimental facts to verify that a given law is correct. So before Newton gave his laws in late 1600s, early 1600s, there was a person called Kepler, and Kepler worked with an astronomer called Tycho Brahe, and Tycho Brahe had a lot of observations done for the planetary systems and their positions, astronomical observations. What Kepler did was he utilized that data and gave three laws that governs planetary motion. They're very particular, and it seems like all planets in our solar system follows those laws. So Kepler stated what happens even before Newton gave his laws. And nobody knew why the planets behaved the way they were behaving. And Newton, what he did was, he did the calculation to show that from his laws, from the exact same laws that I was talking about right now, the laws that governs the fall of apple from the tree, he utilized exactly same laws to prove Kepler's laws. So basically, Kepler said what, and Newton answered why. And this was phenomenal. It's one of the biggest achievements of humankind. And it's also the first attempt when we talk about a theory of everything. The same law that governs an apple's fall is also governing why planets move around the sun, which is amazing and magical. However, moving on, when people started developing better experimental tools and utilizing technology a little bit more, there were a few problems with Newtonian gravity that was coming into view. One of the biggest problems was that Mercury seems to change its orbit over time, slowly, like this. And this is called Mercury's orbital precession. And this was unexplained by Kepler's law, and that's why Newtonian mechanics, nobody knew why. There was also an assumption of something called the ether, which is supposed to be a special medium, which is always fundamental, and that's why it should be at rest always. It's everywhere. It's filling vacuum and everything, and through which light propagates. And that's why it should be a special frame of reference. However, there were a lot of experiments done throughout the earth, and nobody could figure out the substance called ether. And there was another very pressing problem, which is that the velocity of light appeared to be independent of any inertial observer. So it didn't matter if you had a torch and you were running and you were trying to calculate the velocity of light, or an observer who was stationary and watching this experiment happen, trying to calculate the velocity of light, it always seemed to be constant. And this is not the case for other objects, right? Not for everyday runners or joggers. So there was certain things that could not be expressed properly with Newtonian gravity. Then came a person called Albert Einstein. And he started pondering on these properties, and then gave two fundamental axioms or laws, which were the cornerstones of something called the special theory of relativity. So his first law says that laws of physics are invariant in all inertial frames of reference. And the second axiom, let's say, says that the velocity of light in vacuum is independent of the frame of reference. I'll go one by one on them. The first one means that if there are two different observers and none of them are accelerating, both of them can apply the exact same laws of physics. There's no differentiation. If you're running with a velocity, you're allowed to apply the laws of physics. And if I'm sitting stagnant, I'm allowed to apply the laws of physics, the same laws. The second one says that the velocity of light in vacuum is observer independent. No matter if you're running, no matter if I'm sitting, each and every observer, if they conduct an experiment, will come to the conclusion that light travels with the exact same velocity in vacuum. There's also a connecting thread to this, which says that information takes time to travel, and velocity of light in vacuum is the maximum velocity limit of the universe. So before this, our assumption was that gravity was instantaneous, for example. So information or gravity or anything doesn't take time to travel. It's just traveling instantaneously. But now we see, now special theory of relativity tells that information takes a certain amount of time to travel from one observer to the other. And this limit of its velocity, this upper limit of the information travel is bounded by the velocity of light. So let's imagine there are two observers. One is Tom and another is Jerry. Jerry is running away from Tom as usual. And let's look at what Newtonian mechanics tells us and what special relativity tells us. Newtonian mechanics tells us the time is same for both Tom and Jerry. Special relativity, however, says that the time is not the same for both. And this time not being same for both is actually tied up to the reason that information takes time to travel. Newtonian mechanics tells us space and time are completely independent. There's no relation to each other. Special relativity says that space and time are entangled. Now, these two are actually mathematically linked to two types of mathematical transformations. One is called the Galilean transformation, another one is called Lorentz transformation, but I'm not going to go too much into that. And the third point is that Newtonian mechanics states that information travels with infinite speed, and special relativity states that information takes time to travel and it travels with the velocity of light. So to understand time now, why space and time are entangled, I'm just going to do a little bit of thought experiment, which is imagine you have an appointment and you're going to the doctor, for example, and you know where to go, you know the location. So X, Y, Z, you know that. However, you need to know the time, because if you don't know the time, you will never end up at the right appointment. So time is a very fundamental entity that's interwoven, intercorrelated with space. There's a lot of mathematics behind everything that I'm saying, but this is the general takeaway points that we can gain from this. So we actually live in a four-dimensional world where 3 dimensions are our usual notions of X, Y, Z coordinates, and the 4th dimension is actually time. I'll be also talking about something called Spacetime Grid. So imagine you have a graph paper, which usually gives you X and Y, 2 coordinates. If you have a 3-dimensional graph paper, it'll have the Z coordinate. But imagine a spacetime grid. It'll be originally 4D. So it'll be like a graph paper in 4 dimension, where the 4th dimension is actually time. Okay, so when I was talking about time being observer dependent rather than observer independent in special relativity, let's conduct another thought experiment. So imagine there are 2 clocks, C1 and C2, and they're properly synchronized. There's no time delay. They record proper times with each other. And we have 2 observers, Tom and Jerry. And we also have a light source in green over here, which is exactly at the midpoint of C1 and C2 initially. But there's a difference between the 2 observers. According to Jerry, the clocks C1 and C2 are not moving anywhere, stationary. According to Tom, the clocks C1 and C2 are moving, say in the right over here, with a particular velocity, equal velocity. It's moving over time. So now what we do is we give a pulse, emit a pulse from this green light source here. And what Jerry would observe is that the light, it's taking some time to travel, but since the distance is equal for C1 and C2, Jerry will record the 2 events to be simultaneous. The light is reaching simultaneously to C1 and C2. However, for Tom, something different happens. So light takes time to travel, so the beam is traveling, beam is traveling, and C1, it is traveling towards the incoming beam. So it records the incoming beam faster. For C2, however, the other clock, it's moving away from the wave or the light wave that's approaching it. So it records the time when the light wave passes through C2 later. So for Tom, these two events are no longer simultaneous. And this happens each and every day in our regular life. We just do not understand because the speed of light, this quantity, it's very, very high. It's 3 into 10 to the power 8 meters per second. That means 3 and then 8 zeros after that. So that's a lot of zeros. It travels so quickly, we just do not see it happening. And it only becomes observable when things or when observers travel with a very high velocity approaching the velocity of light. Some of the consequences of special relativity is something called relativity of simultaneity. That's the Tom and Jerry story that I was talking about. Another very interesting thing is called time dilation. And moving clocks appear slower. And this is exactly what happened to Fred and George, the initial story that I started telling. It is not just something that is recorded, but even biological age or even our notion of time, it slows down for an observer who's on the earth or on the earth when he's observing another person who's traveling with a very high velocity. Also, we know this equation equal to mc square. And this actually comes from special relativity, which is one of the cornerstones of nuclear power plants. Another thing to be very careful over here is that there is no correct time or there's no right or absolute notion of time. Each and every frame of reference is right and can use the laws of physics. Okay, so moving on, I'll conduct another thought experiment, which is, we now understand special relativity, but we weren't talking about mass at all. And without mass, there's no gravity. So let's insert mass in the whole situation. Imagine I have a box and it doesn't have any windows. And I put you inside that with a ball of certain mass. And now I place the box on Earth. And even though you're not looking outside because you have no window, you have no way of knowing, if you just throw the ball and calculate its acceleration, you'll see it's falling with acceleration due to gravity, and you'll conclude correctly that you're on Earth. Now I'm going to do the same thing, like keep you in a box and close it, but now I'm going to put you on a spaceship and make it move with an acceleration a. So you're no longer on the surface of Earth. However, since it's moving with an acceleration and you conduct the same experiment, you'll see the ball still falls. So, since you're inside the box and you have no understanding of what is happening outside, you cannot differentiate between whether you're on Earth or whether you're on a spaceship. So, at a local frame of reference, gravity and force, they're not different. You cannot differentiate. However, let's do the same experiment. But I put you in a very, very big box, and the Earth is much further away, so you can see that. And I give you 2 balls. And now you do the same experiment, and what you'll see is that if you're on or near the surface of the Earth, the balls actually fall towards the Earth, but they're attracted towards the center of the Earth. So the distance between them actually decreases over time. But when you're conducting the same experiment on the spaceship, you see that the distance does not change. So you're doing the exact same experiment, but now you can differentiate between force, for example, or acceleration and gravity. This is because the frame is no longer local. You're further away. So in a non-local frame of reference, you can tell the difference between what is gravity and what is force. And here we come to another conclusion, which is gravity is the curvature of space-time. And what is that? I'll elaborate a little bit more. So let's go to geometry now, just about what is a curvature. We are used to notions of flat space or flat everything, which we traditionally would call as Euclidean geometry. Euclidean geometry means that you have a flat surface, and how do you know the curvature is zero? That if you draw two parallel lines, they'll never meet each other. And if you draw a triangle, the sum of the angles will always be 180 degrees. However, let's imagine a horse's saddle, and your surface is defined by the saddle, and you're not allowed to move anywhere apart from the surface. You cannot jump onto the space for the saddle. You have to move or following these grid lines. This is called negative curvature, and if you have two parallel lines, they'll get away from each other. It's divergent. And if you draw a triangle, the sum of its angles will be less than 180 degree. Also, there's something called spheroidal geometry. It's like a globe or the Earth's surface. And if you draw a triangle over there, the angles will be greater than 180 degree, the sum of the angles. And if you have two parallel lines, for example, two places on the equator, and you just follows the lines of longitude, they'll meet when they meet at the poles. So basically, parallel lines become convergent. So now that we understand a little bit about what we mean as curvature, Einstein gave his field equations, which told that matter actually curves this grid, this space-time grid, and that's why this change in the curvature of space-time makes other matters to move. So to understand this equation a little bit more, there's a very special quote which says that space-time tells matter how to move and matter tells space-time how to curve. This is not actually one equation. It's a tensorial equation, so there are multiple equations ingrained in it. But the takeaway point from here is that one side gives the matter or energy content of the space-time, because now we know from special relativity as well that matter and energy are interconvertible. And the other side defines the geometry or curvature that we were talking about of space-time itself. So for example, if you have a very taut grid, or if you have a handkerchief, and if you hold it tightly and then you put a very heavy ball on the middle, you'll see it curves that handkerchief in a particular way. Now, if you have a small marble and you throw it on that handkerchief, you'll notice that the small marble is following the curvature because it has nowhere else to go. So what we understand now from general relativity is that gravity is not a force, but it is the very curvature of space-time. Why does the Earth actually keep on moving around the sun in a particular orbit? That is because the space-time around the sun has curved so much that Earth has no escape. It has to follow a particular route. It cannot jump around. So some of the consequences of general relativity, there's something called gravitational time dilation, which makes clocks tick slower in a stronger gravitational field. So when you're closer to the Earth, you will record a different time with respect to an observer who's further away from the Earth. And this is very important for using the GPS, for example, in your phone. We use it each and every day. We use Einstein's equation to coordinate our locations with respect to the satellites and where we want to go. Another interesting consequence of general relativity is something called gravitational lensing, which says that gravity actually makes light bend as well. Why? Because if we look at this grid and imagine the particle moving with a particular in a particular path because it is nowhere else to go, same thing happens to light. Light actually has to follow these grids or space-time curvatures for it to move in any particular direction. So this gives rise to something called gravitational lensing, where gravity is bending and distorting the route of light and acting something like a lens. There are also something called black holes, which I'll be talking about very soon, which says that a sufficiently strong mass can actually deform the space-time so much that nothing cannot escape. So just to differentiate between Newtonian gravity and Einsteinian gravity, we have learned that time is absolute in Newtonian gravity. However, in Einstein's theory, we understand time is relative. It's very much observer dependent. In Newtonian gravity, information travels with infinite velocity, while for special relativity, there's an upper limit to any velocity, and that is the velocity of light in vacuum. And the velocity of light in vacuum is the absolute. Space-time are independent in Newtonian gravity. In Einsteinian gravity, space and time are fused together to one entity called space-time. Matter and energy are completely separate in Newtonian gravity, but matter and energy again are fused together to one equivalent entity. They're interconvertible. For Newtonian gravity, gravity is a force. For Einsteinian gravity, it is the curvature of space-time due to the presence of matter. And at a very weak gravity and at a very low velocity, Einstein's theory reduces to actually Newtonian physics. So Newtonian physics is not wrong. We use it each and every day. It is so powerful that we use it in our everyday life. It is just a limiting case for Einsteinian gravity. I'll talk a little bit about black holes. Black holes are basically dead bodies of massive stars, which can be as big as 20 times our sun. And the black hole itself, it depends on how it is born. So which star is dying and how it's dying will determine how big a black hole be. And it's extremely dense. It's so dense, it distorts space-time so much that even light cannot escape its pull. And it's very interesting for physicists because all known laws of physics actually completely breaks down inside a black hole. If you look at the grid of the space-time grid near a black hole, we see that it's distorted, and this extreme gravity has broken down space-time. And we define a term called event horizon, which is the boundary from where even light cannot escape. So we have no information of what happens inside the event horizon. We just know there's some point called singularity, which is the center, and it has infinite curvature. So space-time ceases to exist, and no laws of physics known acts there. We just don't know what happens. That's why it is so cool. They're pretty hard to observe because, of course, light cannot escape them. So we can't see it, essentially. If you want to fall onto a black hole, it's not a great idea. And it is not as nice as an apple falling from a tree. For example, if I give you a piece of cheese, I'll give cheese because cheese is still quite stretchable, good cheese. And I take it close to a black hole. It starts getting falling onto the black hole's gravity, the gravitational pull. And what the pull does, it stretches it. The cheese is slowly stretched to something called spaghettification. It becomes thinner and thinner, unless then afterwards it's ripped apart. And if a human is falling, it's not a nice sight. So now just imagine we have devised some kind of a special suit that will preserve us. We won't die. And we have Alice and Cheshire Cat. Alice decides to wear the suit and stay away from all the problems that are going to come soon from falling onto a black hole. But Cheshire Cat is very adventurous. And Cheshire Cat decides to approach the black hole. And then once he's approached quite a bit, there will be the gravity working. And so the Cheshire Cat cannot escape the gravitational pull and will start slowly falling towards the black hole. So what will Alice see? Alice will observe the Cheshire Cat to be redder and fainter slowly over time, but it will never actually see the Cheshire Cat cross the event horizon onto the black hole. This is because the information or light cannot escape the surface of the event horizon. So Alice will never actually observe the fall, only see the Cheshire Cat smiling and waving and smiling and waving and slowly fading away, including his smile. The Cheshire Cat, on the other hand, won't see anything special until crossing the event horizon. And if it survives, we have no idea because we are not getting any information back from him. A part of my research is actually modeling theoretically this black hole mergers that might emit something called gravitational wave. And I run my simulations or models, or I do my big calculations in the OzStar supercomputer. This is my supervisor, Jared, in front of the OzStar supercomputer, and this is Albert Einstein looking at two black holes. But what are black hole mergers? What are gravitational waves? That's a story for another time because it's too big to talk about. I'll summarize it with what I talked about today. We learned about gravity. We learned about the evolution of human knowledge over time. We realized physics communicates through mathematics, though we didn't do much of it. But mathematics is like the language of physics through which nature is communicating with us. We realized what space-time and matter was. We understood a little bit about the black holes, and we saw what technological evolution has happened because we have understood gravity better and better over time. I will end up with the future, which is we will understand more and more new science using updated technology. We'll have a lot of telescopes, and we actually, though we cannot directly see black holes, we can detect them in different forms. As I said, that's a story for another time. And with better technology, we'll learn more and more about them. We'll observe the cosmos, not just by seeing, but by listening. That's what OzGrav specializes on, listening to the cosmos. And maybe someday we'll learn what is a singularity really and what happens inside a black hole and why. I will end it with a quote from Rabindranath Tagore, one of my favorite authors and poets. He says that, I seek the unknown that lies amidst the known. So we know some bits about gravity. We don't know a lot, but we use our knowledge to understand it more and more, and we try to decode nature in its true form. Thank you.
Thank you, Debatri, for that talk. So we have time for a couple questions. Now, the first one we have is probably a little bit more of, it's not as much of a science question. The question is, would you go into space to do gravity experiments?
I probably will. It sounds like a lot of risk because we can sit very comfortably on Earth and do use the telescopes and gravitational wave detectors, what we call them, to do the bad work for us and take all the risks and sit at home and do the calculations. Personally, yeah, if I have this indestructible suit, I might risk actually. Yeah.
Very nice. And we'll do one more. So how did scientists first learn that what the speed of light is and that it's constant? Because it seems like it would be hard to measure.
Exactly. It's very hard to measure. But around late 1800s, people were developing better and better instruments. There was the Industrial Revolution, and they were using certain things which is called interference of light, which is a little bit of optics. We have to understand light more and electromagnetic theory, but I'll describe it a little bit. So if you have two beams of light, they have to be quite energetic. And you make them travel to unequal distances and make them meet at a certain point once again. It creates something called an interference pattern, which is like this fringe. It's like a barcode. So this dark pattern, light pattern, like that. And from those widths of how the light and dark patterns are arranged, or how thick they are, we can decode a lot about how the light has traveled and what distance and at what velocity. So there was this interesting experiment by Michelson and Morley, you can look it up, and they conducted this experiment about the speed of light as well as trying to detect ether, this special hypothetical substance which seemed not to be there, it doesn't exist, using this kind of understanding of electromagnetic radiation. Or that's called an interference pattern.
Okay, great. So I think we'll end our Q&A there, but we want to thank you again for such a wonderful talk. And I would like to highlight that we have another OzGrav live talk coming up this Friday. Paul Lasky from Monash University will be talking about NEMO. NEMO stands for the Neutron Star Extreme Matter Observatory and what it can teach us about neutron stars. Now, this is not going to be on our this OzGrav YouTube channel, but in order to find out more information, you can go to the events section of the OzGrav website at ozgrav.org. And we would also like to briefly mention that we will be running some National Science Week events in August with a space and virtual reality live stream event called SCIVR. So that's SCIVR. And you can go to that SCIVR website to find out more, or just stay tuned to the OzGrav socials for information about all of these events. So thank you, Debatri, and thank you everyone for joining us.
Thank you, Jackie.